Okay, so we're going to talk about a few genetics problems here, and what we're going to be talking about is pedigrees and using the chi-squared to show significant difference between the observed and expected values of the alleles. So let's take this first example that we have. We have a cross between purple flowers and white flowers, just one trait being tested. Yeah, so purple flowers must be dominant because the F1 generation is filled with purple flowers. In the F2 generation, we can see that the majority, approximately 3/5 or 2/3, I'm sorry, of the generation is purple. So we can expect 3 out of the 4, since the color purple is a heterozygous dominant trait, we can expect 3 out of the 4 F2 generations to be purple, which would come out to be 112.5 for the expected. And then 1 out of 4 for the white color, which is going to come out to be 37.5 the expected. So a little bit of difference between what we've observed. So how do we test this difference? Well, we use the chi-squared. So the chi-squared is equal to the absolute value of observed traits minus expected traits squared over or divided by the expected traits. So here for the chi-squared, you get 2. Okay. So and then now we got to find out our p-values. So what we do first we have to find our degree of freedom, and with this degrees of freedom, we find that n minus 1. So we had two groups, two traits. So -1 is 1. So if you take that to the table, p is going to be between 0.1 and 0.5. So the conclusion is there's no significant difference between observed and expected trait values. Okay. So that was a little bit of overview. I kind of went over everything all at once, but we are breaking it down here as I use the slides that we got from class. I couldn't think of a better way to explain everything. So again, we're going to make sure that we always make sure that we check for the p-value to make sure that there's no significant difference between the observed and expected values, which in this example is good. We have that. Okay, on to problem 2. So problem 2 states in corn, purple kernels are dominant over yellow kernels, and full kernels are dominant over shrunken kernels. The corn plant with purple and full kernels is crossed with the plant with yellow and shrunken kernels. The following progeny are obtained. So we have purple and full at 112, 103 purple and shrunken, 91 yellow and full, 94 yellow and shrunken. So what are the most likely genotypes of the parents of the progeny? Test your genetic hypothesis with a chi-squared test. So here's what we're going to start. So the first question we have to ask is what information is required to solve this problem? Okay, so we're definitely going to have to know the genotypes of the parents in order to perform a cross to find out the expected trait, the numbers of expected trait values. So with the genotypes of the parents, that's when we come down to expected phenotypes of the parents. So once we find out the genotypes and are able to do a cross, then we can find out what the expected phenotypes are. So what information is provided here to solve this problem? So what it gives us is the observed phenotypes. We don't have the expected, but once we do a cross, we can find the expected, especially now that we still know the amount of cross that is going to occur, which happens to be 400 in this example. So the total number of offspring, as I mentioned, is 400. Okay, so first let's break them apart. Analyze the color and shape. Analyze the color and shape traits separately. So for color, we have a heterozygous dominant purple crossed with the yellow. Okay, so if we cross those, we're going to get a mixture of 50% purple and 50% yellow. And we take over here, if we look at shape, we're going to have 50% full and 50% shrunken. We just have the same heterozygous dominant sets of shape. Okay, so now that we have that, let's combine them together. So if you combine the two traits together, each phenotype with the different combinations possible we're going to get an expected value of 25% of each. Okay, so since we tested 4 different phenotypes, degrees of freedom, remember, n-1. So we'll keep that in mind as we plug in chi-squared. So for the purple and full, we had an observed of 112. We expected 100. Square it and then divide by 100. That's going to give us our chi-squared value. Repeat that process for the remaining 3 phenotypes, and then we add them together, and we find out our chi-squared is 2.7. So if you look on the p-value chart, you find where you use your degrees of freedom, and you find where your p-value is. 2.7 ends up with 3 degrees of freedom between 0.975 and 0.9. So that's good. There's not that much difference between observed and expected. That's exactly what we would hope to see. Okay? And here's problem number 3. Joanna has short fingers, brachydactyly. She has 2 older brothers who are identical twins, both have short fingers. Joanna's 2 younger sisters have normal fingers. Joanna's mother has normal fingers, and her father has short fingers. Joanna's paternal grandmother, her father's mother, has short fingers. Her paternal grandfather and her father's father, who is now deceased, had normal fingers. Both of Joanna's maternal grandparents, her mother's parents, have normal fingers. Joanna marries Tom, who has normal fingers. They adopt a son named Bill, who has normal fingers. Those biological parents both have normal fingers. After adopting Bill, Joanna and Tom produced 2 children, an older daughter with short fingers and a younger son with normal fingers. So that's a long paragraph of a question. So the first thing that I want to do is break that down to a pedigree. And as you can see here, you have the mother having it, the son having it, but the daughter doesn't, and so forth. So what we do is try to find out what is the method of inheritance for the future generations. So what's most likely? My answer is autosomal dominant, because the trait is passed on equally to both males and females. So since it's found in females, we can go ahead and cross out that it's not Y-linked. Now, is it dominant or recessive? Well, it doesn't skip generations, so we know it's not recessive, so it has to be dominant. So could it still be X-linked? Well, it's not passed on to all the daughters from the father, so no, it can't be X-linked. So my conclusion is that it's autosomal dominant. The last part of the question is asked, if Joanna and Tom have another biological child, what is the probability, based on your answer to part B, that this child will have short fingers? Well, if we look at what we have, we determined that Tom must be homozygous, recessive, and Joanna must be heterozygous, dominant. Okay, so it turns out that we have a 50% chance of each for the biological child to have short fingers or long fingers. So there's a 50-50 shot of this child having short fingers. And those are the questions answered. Thank you very much.